understand what I'm speaking of. Okay, so there's also a live stream recording. Okay, that's fine with me. Good. Okay, so let's go. Let's see. So what's the setting that we are in? So we are in a public key world. So I have a public key, which is denoted PK, and a secret key, which is SK, and encryptions of M under the public key are denoted by C, and that's the ciphertext that we have here. And now it's very easy to define a cryptanalyst job. So the job would be maybe secret key recovery. That's the most important goal. So you give me the public key and I have to reconstruct the secret key underlying your scheme. Or you can think of maybe an easier task, message recovery. You give me the public key and a ciphertext and I have to reconstruct the underlying message M. Yeah, so I have three running examples during this talk. So first of all, we have RSA. So here we have a public key N, which is a product of two primes, P and Q, and a public exponent E. Ciphertexts are M to the E mod N. So there's no padding here. It's a plain textbook RSA. That's good enough for our talk. And your task is to either recover the secret key, and you already see there's some redundancy in the secret key. So you can either recover P or Q or this exponent D, which is the inverse of E modulo phi of N, or the message M, right? And then I will also talk a little bit, not too much, about El-Gamal. Here we are in the discrete log setting. So you get a generator G of a group, you get G to the A. Your task in the discrete log setting is to recover A, or you can think of plain El-Gamal encryptions. You get G to the B, G to the A, B times M. And your task is to recover the message, the underlying message M. And this is equivalent to computational Diffie-Hellman. So it's enough to compute G to the AB, and then obviously you can recover M. And then, so in the last half of this talk, I will talk about McAleese, but let's wait a bit. I cannot define this in one line, what a public key and a secret key in McAleese is, but we will also look at partial key exposures there. So, okay, so if this, the script analyst job, given a public key, reconstruct the secret key or the message, that can be really hard, right? And if you look at these problems here, factoring, discrete log, and decoding, can be really, really hard. And here's my favorite quote from Nadia Henninger, who said, so look, factoring is hard, so let's go shopping. Let's do something useful. Don't waste our lifetime in tackling these problems that are too hard. But if they are too hard, so maybe we can do a little bit of cheating. Yeah, and this is what I want to do next. Yeah, if these problems are too hard, we can maybe relax a little bit and get some other useful information from side channels. Yeah, so there's lots of side channels, and these can give us useful information either about your secret key or your message M. And here I listed some of them. So the old school side channels are maybe power consumption, timing, and faults. But there's also cold boot, and many of these partial key exposure attacks are actually called cold boot attacks. Also, there are different side channels where you can get information from. So in cold boot attacks, you are freezing your memory and you want to read out your secret key, for instance, and then you get some faults or some erasures in the secret key. And these are maybe the new ones. They are micro-architectural attacks like flush and reload, or for instance, row hammer, where you also get information about your secret key or your message M. Yeah, and now we are with an easier task, maybe. So we are given the public key and some information about our secret key or our message M, and we have to recover either the secret key or the message M. And usually you are considered especially cool if you do it in polynomial time, yeah? So the question is, how much information do we have to get until we can do it in polynomial time? Okay, and this brings me right to partial key exposure attacks. So what I mean by partial key exposure attacks is very informally, again, our jobs, secret key recovery, we are given the public key and some information on secret key, recover the secret key. Or message recovery, given the public key and the ciphertext plus some information on the underlying clear text message, reconstruct this M. And well, I don't like the name partial key exposure attack so much because it gives you the impression that you are exposing a part of the key, but it's the other way around. So, yeah, so you are getting this information on the secret key or on the M via some side channel, for instance, but then your task is to complete this partial key, right? So it would be rather partial key completion, yeah? Or having a certain fraction of your key, you want to compute all of it. Yeah, but once you have a name, a stupid name in this world, it's hard to get it out again, right? And I think I'm also guilty because if you Google it, many of these papers that are called partial key exposure are actually attached to my name. So I'm sorry for that. But maybe I should be a little bit more concrete what this information means here on the secret key or the message M. So this information can be, and I will start with that in a minute, could be some bits in consecutive positions. It could be some bits in random positions. It could be all of the bits, let's say, of the secret key, but some of the bits are flipped, or it can be many other things. Yeah. And I want to discuss with you some intuition that will become important also during this talk. Yeah, I will go back to this intuition several times. So the intuition is as follows. If I give you a secret key, this secret key has n bits, and I leak you k bits out of these n bits. Then recovering the whole secret key should be as hard as I would initially chosen the secret key of n minus k bits. So it should somehow reduce the dimension of the secret key, right? Because I leak something, but it should still retain the hardness of it. So it should not really collapse down to something easy. And what I find fascinating about these partial key exposure attacks, and I hope you will also find it fascinating during these talks, sometimes this intuition is plain wrong. So I leak you some of the bits, and then the remaining problem becomes very easy. Yeah, it's like solving a riddle. I give you a partial solution of this riddle, and at some point you say, oh, look, now it's super easy for me to solve it. Yeah, and the same happens here in crypto. And sometimes it happens, and sometimes it does not happen. I will also give you counter examples, and I don't really know why this is the case. Huh? That's a good question. So let me first give you examples where security breaks down. And here's one of the most prominent examples of these. It's a 26-year-old attack. So very old results for you, but I also have some new for you. Okay, so here's a famous result of Coppersmith that tells you the following. I give you a plain RSA ciphertext. Encryption exponent is 3, so C is M to the 3 mod N. And now your task is to recover M, and I give you 2/3 of the bits of M in upper positions. Yeah, let's model this. So these are the upper bits. These are 2/3. So think of, for instance, N is 1000 bit. Then this tilde M is 667 bit. Yeah, and the low order bits I model as X. So they are unknown. These are 33 bits. Yeah, and once I have this, I can also write it as a polynomial. Yeah, so this is a polynomial equation, and it has a root or a 0, which are the low bits that I'm looking for. And this equation here holds mod n. And then there's this beautiful Coppersmith method, which is based on LLL reduction. And it tells you once you have such a polynomial of degree 3 modulo n, then you can actually find all roots in polynomial time, provided that the roots are somehow small, so they should be smaller than n to the 1/3, which is exactly what we need, right? So we have 2/3 of the upper bits, and we get the other 1/3 for free. And this looks pretty cool, right? Because these low order bits, they can be like 333 bits, and we get them in polynomial time. It's a huge search space, but still we can do it in polynomial time. Yeah, this is pretty cool. Or wait, maybe it's not so super cool. Let's look at some special case of this, right? So what happens if I don't know the upper bits, but I know that the upper bits are 0? Yeah, so M itself is small. Yeah, so M is, let's say, 333 bits. Then if you do encryption, plain encryption of it, it's smaller than 1,000 bits. So the C is really M to the 3, but not mod n. It holds over the integers, which in turn means that having C, you can just compute the cube root and you recover M efficiently, also in polynomial time. Yeah, so that means there's a trivial case of this attack where the upper bits are not known, but they are 0, right? And the theorem here above, it basically extends this trivial upper case where the upper bits are 0 to the more general case where they are not 0 but known. Yeah, and this is very important then to understand these partial key exposure attacks. This is often the case. So you have like a base attack. It mustn't be trivial, this base attack, like something is small. And then you extend it to the case where it's not small, but you know the bits. Right? Questions up to this point? I don't see any. Maybe I also look at the chat. Okay, nobody dares to do something in the chat. It's also fine if you ask some questions in the chat. So I will look frequently into that. Okay, good. If there are no questions, I continue with a second theorem, second most important theorem from this time from Coppersmith, also very famous. It's called factoring with high bits known. And it says you the following: if you have an RSA modulus and is a product of P and Q, then P can recover, so the factorization can be recovered given half of the bits. Let's think of the upper bits of P again, half of the bits of P. Yeah, again, we model it. So N is the upper bits of P plus X, which are the lower bits of P, and Y, which is Q. And again, we write it as a polynomial. Now it's a bivariate polynomial in X and Y, and it holds over the integers. And then there's another theorem of Coppersmith that tells you, well, if you have such a bivariate polynomial over the integers, then you can find all roots satisfying that they are somewhat small. So X times Y must be smaller than N to the 3 over 4, which is true here. So X is N to the 1 over 4, Y is N to the 1/2. So this is fine. And now you should be somehow fascinated by this result without any crumbling, because there's no simple base case, right? There's nothing trivial here in this result. This is just a polynomial time attack without any simple thing around. Okay, so, but if you think of partial key exposures, then usually in RSA, you do not leak bits of P, right? This is, if you think of real cryptanalysis, you would work with the secret key, the secret exponent D, and there's also plenty of results for the secret exponent D in RSA. So here it is. So you know that the public exponent E and the secret exponent D, they satisfy this equation. They are the inverse modulo Euler's totem function phi of n, which is P minus 1 Q minus 1, and you can rewrite that, right? So this mod you can write as some K times phi of n, and phi of n itself is this term just written as n minus something unknown. Yeah, and now you have a polynomial again, so you can make it a modular polynomial, and this was done by Wiener. If you take it mod n, then this term here cancels out. You get E times D, which is modeled as E times X, minus the rest, right? So the rest is this 1 and K times this bracket here. Yeah, and if you work out the details, that's basically simple, then you can easily show that this D is smaller than N to the 0.25, which in turn means if you have a 1000-bit N, then you can recover in polynomial time your secret exponent in RSA if it's less than 250 bits. It's again kind of impressive. So, but you can also reduce this equation here, not only modulo N that you know, but you also know E. If you do it mod E, then you come up with this equation, right? So the left-hand side cancels, and you get 1 plus the x is now k, and the y is this term. And then you can, again, analyze that, and then you get a better bound. Yeah, you get n to the 0.29, which, again, our example, if you have a 1000-bit n, then you can recover d if it's smaller than 290 bits. That's very impressive. And this is now the base case. These are small d's. And now you can ask the question, what happens if d is not small, but you know some bits of d, right? Let's say the upper bits. And this was done in this work here at Eurocrypt 2005 by Ernst Jochems, myself, and De Vega. And we show that you can extend this Bonney-Duffy thing. And this was not optimal, and there were several nice contributions to make it much smoother by Takayasu and Kunihiro starting from 2014. Yeah, and maybe some personal remark regarding this Bonney-Duffy, because it was kind of the starting point when I started research in cryptography, and there was a claim in this paper. Yeah, so Bonney-Duffy claimed that this cannot be the true bound, this 2.9. It's too unnatural, and there were some arguments that the true bound should be d smaller than n to the 0.5. And this kind of fascinated me, and I thought, look, these Stanford guys, they are so smart. This must be true. Let's do some research and try to prove this bound. And I miserably failed within the last 25 years to improve this bound. But on this way, I showed some other things. And maybe this is how research works, right? So they stimulated lots of research in this area, making this claim. And also, I'm pretty sure that it's not true. It just produced lots of results in this area. So sometimes it's good to make wild conjectures. And it's even better if they are not true, right? So it's also hard to disprove this conjecture. Okay, so more of these results. So usually in RSA, you are not even using D as a decryption exponent, but what you are instead using is so-called CRT. P-1 and Q-1. These are called CRT exponents, and there are more results on that. So if you have small secret dp/dq, which satisfy this equation here, then there's an attack of Alan Jochems and myself from 2007. I think this was Eurocrypt. And we showed that they should be smaller than this. So you see the bounds here are a little bit smaller than in the D case. And then it took 10 years until this super nice result of Takayasu, Lu, and Peng, who showed actually at Eurocrypt 2017, like 5 years ago, that you can kind of dramatically improve this bound, right? So first they showed at Eurocrypt it's 0.9, something like this. And then they made a journal version, and they even showed this bound, 0.1 to 2. And I have seen many of this Coppersmith stuff within the last 20 years, but this one is very involved. So it's really complicated, but it's also very nice. So it uses the geometry of several polynomials, and we tried to understand this attack, and it took us a long time to actually really understand what's going on in this attack. And then we could actually do also RSA partial key exposures where dp/dq are not small, but you have known bits. And this is the extension here with my co-authors, Julian Nowakovsky and Santanu Sakar. And we could do that as a partial key exposure. And then we got excited also about these CRT exponents. And this Eurocrypt, we showed some very strange result, I think. So what we showed is, if I give you 1/3 of the bits of dp/dq, then this is enough to factor n actually, or to recover all of dp/dq in the case that E is roughly of the size, it's n to the 1/12. So it indicates that partial key exposures are actually easiest if E is somehow smallish, but not super small. This is completely against my intuition, because I thought that RSA is actually easiest if E is constant. But this is obviously not true if you look at this result. So I think it's very strange, but also very fascinating. Yeah, and you need really a small amount of bits of dp and dq. Yeah, here's some remark. So all partial key exposures that I look now at RSA, they so far require, they so far require some strong setting. So the bits that you get are error-free. There's no errors in, and they are in consecutive position. So either you get the most significant bits or you get the least significant bits, and then you recover something. Yeah, but there are also other settings, and one of the nicest algorithms that I know in this area is due to Henninger and Shacham from Crypto 2009. If you want to see a very simple algorithm in this partial key exposure settings, then please start with this one. So it factors n given like 57% of the bits of P and Q in random positions. And the algorithm is super easy. So what you do is you look at all candidates, P and Q, that satisfy the equation that P times Q is n, and then you look at this equation mod 2, mod 4, mod 8, and so on. If you do it without any knowledge of bits, then the number of P's and Q's grows exponentially, right? Because there are so many possibilities for P's and Q's that satisfy this equation. But if you have some P's and Q's in random positions, then you can kind of cut the search tree that you get. And the analysis of Henninger and Shacham tells you as long as you have sufficiently many bits, this becomes actually polynomial time. So this is very nice, and this was extended with Wilco Hennecker and Alex Meurer and myself at Crypto 2010, and we showed that you can also do it in an error setting. So I give you all of P and Q, but some of the bits are flipped. So let's say 8% of the bits are flipped. So if it's a 1000-bit n, so 1000-bit, so 500-bit P and Q each, then like 8% is like 80 bits are flipped. Yeah, so this is still huge in number of bits. So you cannot really enumerate them, but you can do some algorithms here. Okay, so that's basically all I wanted to say about this Coppersmith partial key exposure things. There are several surveys if you get interested in this area and you want to learn more. So first of all, these are only those that were written by myself. So the first is actually my PhD thesis, which can also serve as a survey. The second one was written in honor of the 25th birthday of the LLL reduction. And the last one was written in honor of the retirement of Ian Lenstra, and people asked me to write a survey on cryptanalysis, and I said, look, I can write about this decoding algorithms that I did. They are somehow beautiful. I write a research about that, a survey about that, and they asked me, no, we want you to do Coppersmith. And I said, no, please don't do Coppersmith. I did it for so long. But eventually I ended up writing another survey. So there's a third survey now about this Coppersmith method, and it's actually for beginners. So if you want simple examples about how Coppersmith works, then please read the third one. Okay, so I don't want to do Coppersmith again, but somehow it haunts me. Yeah. Okay. That's it for RSA and Coppersmith. Are there questions so far? I look in the chat. The chat is quiet. Okay. So let's go maybe to the discrete log area. So if we were so successful with RSA, maybe we can do the same in discrete logs. And the answer that I give on this slide and the next slide is kind of frustrating, right? So in the discrete log setting, all this stuff it doesn't work, right? So let's start here. So discrete log, you get a discrete log instance and a public key, let's say from El-Gamal, it's G and G to the A, and let G be of order Q. So let's say it has n bits. Okay, and then there's the well-known Pollard-Rowe algorithm from 1975, and its complexity is the square root of this order. Okay, so you have a square root algorithm, it's an exponential algorithm, and there's also a small secret thing, yeah? So if your secret is small, so think of like the Wiener and Bonidavi attacks, let's say it's k bits, much smaller than Q, then this Pollard lambda algorithm, which is in the same work of Pollard, it works in square root of 2 to the k. So it's again the search space and the square root of it, right? But nothing better. Yeah, it doesn't really collapse. So think again of our intuition. If I give you the upper bits, like n minus k bits, then it still retains its security, right? The security is still the square root of the size that you have. This is exactly what you want for partial key exposures. Yeah, and there's also very trivial partial key exposure. Not sure whether it's noted in the literature, but it's also trivial, right? If I give you the upper bits, right, A is not small, I can simply strip them off for discrete log setting, right? So if I give you, for instance, the upper bits in form of, again, this tilde A, I can divide by g to the tilde A, and then the exponent, I subtract them off, leaving an exponent which is small, and then I can use Pollard lambda method, right? So again, if I give you the upper bits, you can recover A in this complexity, but that's it. It doesn't collapse, yeah? Unlike in the RSA case, where you really got a polynomial time attacks. And here in this work with Andre Esser, which was at Eurocrypt 2 years ago, we were asking ourselves the question, so what if I give you bits in random positions of the discrete log, and then you can show, similar as in this, you get a low weight discrete log problem, but here the algorithms are even worse. You don't even get the square root of the search space, but something worse. So this is, from a cryptanalyst point, is very depressing, right? I give you information about the secret key, but nothing breaks down, nothing polynomial. So why the heck does it that with discrete logs? Yeah, it seems to be way more resistant towards partial key exposures. So let me look at computational Diffie-Hellman. Yeah, maybe things are better there for a cryptanalyst, and actually it happens to be a little bit better. So if you look there. So let's recall the computational Diffie-Hellman problem. You are given G to the A, G to B. You have to compute this Diffie-Hellman key, G to the AB. And then there's an algorithm of Bonnet-Venn-Kattesan, which is called the hidden number problem algorithm. And this algorithm works as follows. Given an algorithm that gives you the most significant bits of this Diffie-Hellman key, then you have an algorithm that computes all of it, this G to the AB. Yeah, and you can view this as a partial key exposure, and it was very successfully applied for DSA signatures with small bit leakage per signature, but usually you need like hundreds of signatures to do that. There's lots of research, especially in the security area, but also in the cryptographic area. So a recent paper would be Albrecht and Henninger on this problem, but there are many papers on this. But once again, this discrete log seems to be still way more resistant to RSA. It may more resistant than RSA. And the conclusion of many people for this is that this partial key exposure is really an RSA artifact, right? It's really true for RSA that sometimes it really breaks down. So I leak you some bits and you get polynomial algorithms, but it's not true for all the other crypto systems. It's really kind of, you can consider it a weakness of RSA. And my question is in this talk is this belief really true? Is it really something that we only have for RSA, or did we just miss it for other crypto systems and so on? So what is especially interesting now is, I mean, all this world is now working on post-quantum algorithms. So let's look at post-quantum algorithms. What have people done in this area? Is there any partial key thing or not? Okay, so the common belief is now that most post-quantum systems are not really vulnerable to partial key. Yeah, it's like in the discrete log setting, you leak some bits and you lose some dimension, but that's it. Yeah, and some of the results that we have in this area, some initial results, also indicate this exactly that this intuition is true. So there are some called cold boot attacks on ring and module LWE keys under the NTT from Chess 2018 by Albrecht, Eo, and Patterson. And these are also kind of weak from an attacker's point of view, in the sense that you need a lot of information to really get the keys. And the same is true for the Crypto 2020 paper of Dachmann Solé, Ducal, Gong, and Rossi. It's called LWE with side channel with side information. It's in this estimator business, and they show if you leak you a certain number of bits, here these are usually modeled as inner products, then actually your lattice dimension decreases, but that's it. Yeah, there's no complete break of the scheme. So it's just like in this discrete log setting. But there are also more recent papers. So there's a paper together with Andre Esser and Webel and Weng. And this is a partial key exposure attacks on Bike, so a code-based scheme, and Rainbow, a multivariate scheme, and Entrue. And there we showed some non-trivial partial key exposures in this code world. And we also showed that in the multivariate, you don't need so much information, but we also confirmed that in the lattice world, it's somehow worse from an attacker's point of view, right? So it's basically, again, a dimension reduction that you achieve. Yeah, and there's the most recent paper, and I want to talk in my remaining time on the results from this, from Ms. Elena Kirshanova. And it's about the McAleese scheme and also partial key exposures in the setting. Okay, so I would jump now to McAleese as promised on the first slide, unless there are any questions, and I don't see anybody so far. Okay, so let's jump to McAleese. Yeah, so I want to speak about the McAleese crypto system as it was initially proposed in the late 70s, and also about the newest standard, which is called Classic McAleese, which is now probably going to be standardized as well. Okay, so the security of McAleese is based on the hardness of decoding binary linear codes. So I have to explain you what a code is, but it's kind of simple. So a binary linear code, let's call it C, is a k-dimensional subspace of f2 to the n. So what does that mean? So I can express this code in terms of a generator matrix. Yeah, this generator matrix has k rows. Yeah, every row has a dimension n, and the C is the span of this G. Yeah, the row span of G. Yeah, I can take all 2 to the k combinations of these vectors, and then I get the whole C. But for the remaining talk, you should think of you can also define it via the dual, and that's what you do. So you should think of the parity check matrix H, and this has a codimension n minus k. So the dimension here is k, so the dual has a dimension n minus k, and I will call it the codimension. And you can also write C as the kernel of this matrix H here. Yeah, it's the right kernel of this matrix H. So I define this code via H, and then the code words are those linear combinations of columns of H such that the linear combination is 0. Yeah, and that's it basically. Yeah, that's also our computational task. In the remaining, I give you H, and you have to compute C's, which are 0. And this is very tough for decoding because C is usually of very small Hamming weight. So the number of ones of C is small, but in general, it's easy, right? If I give you an H, it's easy to compute the kernel of H. You know, if you do not restrict to small C's, this is also important. So in classic McAleese, I have to define you the key. So SK is a structured parity check matrix H of some Gopper code. And usually people tell you, okay, Gopper codes are complicated, but I hope to convince you of the opposite on the next slide. And the public key is what people call a randomly scrambled version of H. And in a minute, I will also tell you what I mean by randomly scrambled. Yeah, and to give you some parameters, so in McAleese, if you define it for 128-bit security, then the dimension of your vectors is quite huge. So n is around 3,500. And the codimension is 768. Yeah, so the parity check matrix here for our code would be 768 codimension Yeah, that's the number of rows that you have, and the number of columns is 3,488. Yeah, just to give you an impression. So these are kind of huge matrices. And here I did a strange factorization. So this number here, it factors in 64 and 12. And these terms I call T and M, and it will be clear on the next slide what I mean by that. Yeah? So recall T and M. So T is 64 and M is 12. So what is M? Let's start with that first. So the setting is as follow. We start not with the field F2. I will come to F2 in a minute, but I will start with some larger field, F2 to the M, and this M is 12 in our case. Yeah? So that's the M from before. So we have a field with 2 to the 12 elements. Okay, I call that a large field. And I give you a list of n polynomials. So think of this n as before, the dimension of your vectors. It's 3,488. And now I define Gopper points. They are called alpha i's. And these Gopper points are from the large field. Yeah, so each Gopper point is 12 bits. And then, and now it's a second parameter t. So we had t and m on the large slide, you remember. Then I define an irreducible degree t. So in our case, t was as 64. So the degree of my polynomial is 64. And this polynomial is called the Gopper polynomial gx. Yeah, and this has also coefficients in the large field. So is it clear so far? Any questions? I don't see any. Okay, good. So let me define what a Gopper code is now. And you see actually the definition is very brief and maybe also simple. Yeah, just given these Gopper points, is let's say 3,500 Gopper points, and our Gopper polynomial, the set of code words is the set C such the coefficients of C, so the entries of C satisfy this simple equation. Yeah? The coordinates sum, like the sum over the Ci's over, and there's a linear polynomial x minus alpha I is 0 mod gx. Okay, and since gx is irreducible, all these inverses here, they exist. Okay. And now a McEley's secret key is simply this set of Gopper points and the Gopper polynomial, right? So if we think of like partial key exposures, then maybe, yeah, I will start with what happens if I know L but not G. Yeah, this is the first partial key exposure that I have for you. But I still have to explain you what a McEley's public key is and what actually a parity check matrix is, right? Because I was speaking about defining codes by a parity check matrices, but now I define it over this equation here. So this equation easily translates in a parity check matrix, and this is what I did here. So by the way, be careful because this equation can be somehow puzzling. Yeah. So gx is defined over the large field. Yeah. So these alpha i's are also defined over the large field. Yeah. So they live in F2 to the M. So these are really polynomials over the large field. The ci's themselves, they are over the small field. So they are really a subfield. Yeah. Yeah, so think of the ci's being in 0, 1, but everything else is in the large field. So this really makes sense. Yeah, this equation here. So it's really over the large field. And that's why we also start with the large field for the parity check matrix. And here I wrote this. So I have parity check matrix, which has T columns and N rows. And every row is actually only dependent on alpha I. So the ith rows is only dependent on alpha I, right? And then it gets multiplied by, well, g to the minus 1, evaluated at the point alpha I. Yeah? So still every ith column of this matrix is only dependent on alpha I. It's super structured. Yeah. And this is good for us as script analysts. Huh? So maybe we can use this structure. Yeah, but still we are living over the large field. And I promised you that we look at binary codes. So we have to go to the small field, and this we do via some canonical mapping. Yeah, so we can define a basis of this as an F2 vector space, and then we can go to this. So basically what we do is we expand every entry of this matrix to m entries in a standard basis. Yeah, so that also means that from going from T rows, every row gets expanded by m, by a factor of m. So we get to actually Tm rows in this matrix. And this is our codimension n minus k that we had from before, right? So this fits. And now we are over the base field F2. And that's our parity check matrix. It's not yet scrambled and still structured. And in order to destroy the structure, we do a partial Gaussian elimination. So we, in this parity check matrix that we get after this transformation here, we do a Gaussian elimination such that we get the Tm times Tm identity matrix on the left-hand side. But that's all already, right? So this really defines as a public key. So we get a parity check matrix from this code, and this in turn allows us to get some code words of the code, yeah? And this is used in our attack in a minute. Okay, so let me come to a first partial key exposure attack. It was never called such a partial key exposure attack, but it's very well known. So if you look in the literature, this is cited several times. As usual in the crypto literature, you don't find proofs. And actually, together with Elena Kirshanova, we gave a first proof of that. But I think it's also a kind of a known how to do it. Yeah. So you get as input your public key, right? And you get partial information about the secret key. You get all the Gopper points. Yeah, these are 3,500 Gopper points for the smallest instance of Macaleese, but you don't know the GX, and your goal is to recover this remaining part of the secret key. Yeah. Okay. So what you do is now you compute a code word C that lies in the right kernel of this matrix. And this is actually easy to do, right? So we know this age is 700 something times 3,500. So it's very easy to compute this kernel, and there are lots of C's in this kernel. So just take any of these C's and you're fine, and this is a code word. Yeah, it doesn't have small weight, but you don't care. So what we do next is, since the C is a code word, we use the defining equation of our Gopper code. We know that for every C, it holds that this is true. Right? Okay, these denominators, they are kind of annoying, so let's get rid of them. So what I do is I multiply by the product of all x minus alpha j, and then I end up with this, right? So all these denominators, they cancel, and you cancel out one of the factors here in this product for every term, right? So once again, the CIs are plus minus 1. So sometimes you get this polynomial, yeah, you get a sum over these polynomials depending on the CIs, and the sum over all of them is a multiple of GX. That's what we have here, right? And these are polynomials of degree n-1, right? Because we canceled on J, which is equal to I. Okay, so in total we get like a polynomial of degree 3,500 here on the left-hand side, and we know it because we know all the Gopper points now. Yeah, we don't know GX. But what we do now is we compute this left-hand side, and then we simply factor it. Yeah, and among these factors, we factor it into irreducible polynomials, and among these factors, there must be a degree T irreducible GX. Yeah, what I don't tell you is it's not so clear that it's unique. I will come back to this point again later. And in fact, it is not always unique, but that's also not a problem. Yeah, you can also live with a list of several potential candidates for GX, and then you find out which one is your right one. Yeah, so it's not a problem, but you will see some numbers later because we really did it. And sometimes if I speak about this attack to other people, they're actually surprised that you can do it in polynomial time. Yeah, so factoring polynomials over some finite field is actually doable in polynomial time. There's some proof also depending on lattice reduction. Yeah, you can, for instance, do it with LLL, but there are also other algorithms to do it. So we use some Berlekamp algorithm to do it. It's actually very efficient. You will see in a minute. Yeah, okay. So that's already a quite nice result. So a first partial key exposure attack. Now let's improve that. Yeah, and this is the first result that we have in our paper. So what we show is on input the public key from McAleese and some alpha I for some index sets that you know. Yeah, so for instance, I give you the alpha i's in position 2, 5, 7, 10, 12, I don't know. Yeah, but I give you only a few of them. Yeah, I give you only the codimension +1. Yeah, so remember that was the 700 something out of the 3,500. So it's very few points that I give you. And I pretend that you can still recover GX in polynomial time. Why is that? So what we do is we look at the restriction of the public key on those columns, on those positions from this index set I that we know, right? And as I told you, in the i's column is only dependent on alpha I, on nothing else, yeah, in this reuse. Okay, now I know Tm plus 1 columns, yeah, I look at the restriction of H on these columns. And if I look at the right kernel of this matrix, then it has Tm plus 1 columns, but these are only of dimension Tm. So they are linearly dependent, so the kernel is non-trivial. Yeah, so I can compute a C prime, which is not 0, which lies in the right kernel of this matrix. And then I can expand the C prime with zeros in all the other positions that I haven't looked at. Yeah. And then I get a code word again that satisfies this equation. So parity check is times C is 0. So it's really a code word where the support of C. So what is the support? It's the positions where I have ones in C. And the support is only in the index set I that I know. Yeah. So what we have done is we constructed a code word which have ones only in those positions of I that I know. Yeah, I know the positions of these alpha i's. So now I do the same as before, the same argument. Yeah, so now I have a code word with few ones. Yeah, not random ones in any position, but only ones in this index set I that I knew. So now I have to sum over the Ci over x minus alpha I. That's a definition of a Gopper code. But now I can sum only over my index set I because I know outside of this index set I have zeros anyway. Right? Yeah, I can cancel now these denominators again by multiplying by those j that are outside, that are inside I, my index set I, and I come up with this equation. Yeah, it's very much the same equation that we had before, except that the sum is now not over all points, but over all points in I. And these points, of course, I know, right? And then I can compute the left-hand side, which is now a polynomial of degree Tm. So it's even better. So it's a smaller polynomial. I can factor it more quickly. And among the factors, irreducible factors of this polynomial, there must be this Gx. So let's do that. Yeah, so let's do that in practice. And here we did it in practice. And before I come to this experiment, let me give you the observation. So the improvement from our new result is really from our capability of computing code words of small weight, right? Since we had small weight, we can concentrate on this position where we have some weight. So support of this code word, and the weight was at most Tm plus 1. So we could really improve. So here in this table, I give you all McAleese instances for the parameters sets that were suggested for standardization. So this is the smallest parameter set, this is the largest parameter set. This is the codimension of the code plus 1. And then we ran 2,000 experiments, and we averaged over all experiments, and we looked how often it happened that we had a unique GX, so a unique polynomial of degree, in this case 64, in this case 96, and so on. And you see in almost all cases we had a unique L. But if I give you one more point, yeah, one more known point, then in all of them I had a unique GX. So, and the reason is that we get a larger kernel, and this helps us to exclude 40 GXs. And if you look at the runtime, that it's surprisingly fast, right? So this factorization of polynomials. So for the smallest thing, it was in length in 18 seconds on average. And even for the largest instances, it was in less than 2 minutes to find the Gopper polynomial. Yeah. So what we have achieved now, we were given only 700 something points, and then we could recover the Gopper polynomial. But now to recover the whole secret key, we have to recover the remaining 3,488 minus 769 points. And this is what we do on the next slide. So let's see how that works. Yeah, so on input, the public key H, the points in our positions I, again, this is codimension +1. And now we have already the Gopper polynomial. I pretend that we can recover the remaining points also in polynomial time. So what's the idea of that? So again, we construct a code word given the public key, and the code word now has ones in positions in our index set I that we know, plus one position outside of this index set, and let's call this position R, and we construct the code word such that the R's component of this code word really has a 1 there. Yeah, what happens now? So if we are capable of constructing this, and this again only linear algebra, so there's nothing else, then we again have this equation that the sum over my index set I, Ci over the Xi is 0. Now I know all of these terms except for one. So put this one, the R's one, on the right-hand side. Yeah, but now there's a difference because I know GX. So what I do now, I can compute the left-hand side of this. I can compute all the inverses of this, and then I get a polynomial here. And if I take the inverse of this polynomial, then it's a linear polynomial x minus alpha r. So don't care about the minus, we are in characteristic 2, and we can right away read off alpha r, and that's what we do, right? So we construct position by position, we construct these alpha r's, all the remaining points by using this equation and by computing the left-hand side and inverting and the reading of the alpha r. That's it already, right? So let's see it in practice, how this works. And here are the results, again, for the suggested parameters. That's for McAleese. So we are given these points. We reconstruct the remaining 3,488 minus 769 points. That's still a lot. It's like 2,700, something like this. And this can be done in 42 seconds. So it's also super fast, right, to recover all these points. So in total, as you recall, it was 18 seconds to recover the Gopper polynomial, 42 seconds for recovering the remaining points. So it's 1 minute in total for the smallest parameter set, and for the largest parameter set here, this is like less than 3 minutes, or around 3 minutes. Yeah. Okay. Okay, so you see it's super fast, yeah? So the takeaway from this new partial key exposure is we recover the McAleese secret key with roughly 1/4 of its bits. Why is it roughly 1/4? Well, here it's 700 divided by 3,500. This is roughly maybe 1/5. Here's around 1/4. Here's again between 1/4 and 1/5. Here's more 1/5, right? So it's really a small amount of bits that we have to know. Yeah. if you think of RSA, for instance, then we had like three-fourths of the bits were known, and we could recover the remaining 1/4. So here it's the other way around. So we really need less information to do it. It works for random known positions, so that's also somehow different from RSA, where you really had consecutive positions, and for random you had a worse result, so you needed more bits. And it's also, in comparison to RSA, it's super fast, right? So even for the smallest parameters, it's like 1 minute, and even for the largest, it's less than 5 minutes. Yeah, so Coppersmith is also polynomial, but it's not at all that fast. So it sometimes takes hours or even days to compute these lattices. Okay, so how am I doing in time? I think kind of fine. So let's wrap up. So what's the lessons learned in the open questions? So some schemes allow for efficient partial key recovery, and the examples are RSA. And now we have more examples like McAleese, and also I spoke of Pike and so on. And if you compare this McAleese attack with RSA, then it works with way less information in random positions and faster. So you can really do it in minutes. And we did it on a laptop, so it was not a computing cluster or nothing. And some schemes also seem to be more resistant, right? So discrete log, we hardly have anything. Yeah, and also for lattices, we merely have dimension reduction. There's nothing breaking down. And also, if you look at lattices, for instance, LWE, they are way less structured like this parity check matrix. Yeah, if you think of the attack now, we really use the structure of this parity check matrix, such that the ice column was only dependent on the ice copper point and so on. Yeah, and my conjecture is the more key redundancy. So the more redundancy you have in your secret key, the better are your partial key exposure attacks, right? And for code base, this is you have more redundancy because there's a code behind, and this is structured, and this really helps you in these partial key exposure attacks. Yeah. So our results, for instance, show that you can easily compress a McAleese secret key by a factor of 4. And you're still polynomial time. Yeah, you can work with that. You could easily recover the remaining thing. Maybe in practice, you don't want to spend 5 minutes to actually expand your key again and decrypt, but this in principle you could do. Yeah, and there are some questions now. So, well, can you improve on this McAleese result? So obviously, if you are capable of sampling low-weight code words, then you could, but we don't know how to do this in polynomial time so far. And also in McAleese, to be fair, these alpha i's are usually encoded in a Banach network, and then I don't know how to do this if I don't have them in the clear, these copper points. Yeah, and also how to extract these alpha i's in practice. So for now, I assume that I just get them by some side channel, but it's not clear to me that you can really do this in real side channel attacks. But there's also some chess work this year that shows that you, in some cases, you can really do that. Okay, so I think I'm just fine in time, and this is the end of my talk. So thank you very much for listening, and I'm happy to take questions if I have enough time to do so.
Thank you for the talk. Any questions or comments? Here. Hi, sir. Sir, I want to know, during the design of any crypto algorithm, what should we take care to avoid such attacks?
Oh, I'm very sorry. I'm afraid the quality of the micro is not very good. So maybe there's an option to write it in the chat. This question.
Can you hear us, Professor?
I can hardly hear the micro. I'm very sorry.
Somebody can type.
It's kind of interrupted, the micro. I sincerely hope that my audio quality was better than the micro that you have. Is there a chance to put it in the chat, the question?
Hello, sir. Am I audible?
Yes.
So you can ask questions, sir.
Sir, this key redundancy is a generic criteria or only for MACLIS?
I'm sorry, I don't get it. Once again, could you write it in the chat, or could you? It's really interrupted. Or can maybe someone with a better micro repeat?
How to avoid such data? Implement design.
Oh yeah. Oh, you're. Oh, I think okay. That's a good question. Yeah, yeah. Is it conjecture that I do here on the last slide? Is it a generic or is it only for McAleese? I think it's a generic. So what I think is the more structure you have in your system, the better are the partial key exposure attacks. So I would expect that we find many more partial key exposure attacks for many schemes, as long as we use the key redundancy. So it's not really an artifact of RSA as people believe. So I think it exists in many places, and you see it now for McAleese, right? I think that people never studied this before because maybe, well, McAleese was always important, but now it gets standardized, right? And then people look more closely into it, and they are kind of copying attacks that we had before. And I would expect that we see more of these types of results in the near future. Also, if people start to study more side channel attacks on these schemes. That's my impression. So it's not really for McAleese, but McAleese is kind of heavy because it's such a heavy structure, right?
Yeah, okay. Let us thank Professor May again, giving him a black clap, and they're going to start the thing.
Thank you very much. It was a pleasure.
There is a small announcement. Those who want to buy ink, there's a they open table on site, so you can have it.
Sir, can you please stop screen sharing? Thank you, sir.
Había algo জিজ্ঞেস করবো কি সেশন জিজ্ঞেস করবো আরামসে আরামসে জিজ্ঞেস করবো আরামসে তুমি বলেছিল হয়তো অ্যানাউন্স করি
আরে এতগুলো কেন খোলা আমি তো বুঝতে পারছি না। হ্যাঁ এবার হচ্ছে, তাহলে আগে মৃদুলদাকে অ্যানাউন্স করতে দেয়, মৃদুলদা অ্যানাউন্স করছে কিনা দেখ।
আওয়াজ শোনা যাচ্ছে তো?
প্লে করবো,
আওয়াজ শোনা যাচ্ছে তো?
প্লে করবো,
কি আওয়াজটা শোনা যাচ্ছে না?
ঠিক আছে দেখ এবার। পোস্ট করবো, কি বলছে রোদ। কি করবো?
দাঁড়িয়েছে।
And for the first one, the authors are not here. In fact, they are online also, so they have sent a video. Video. So the first talk of improved content differential distinguishing of AES with complete F-box, and it is by Chen Chan, Mutant One, Link Zone, and Poet One, and Chen Chan video will be presented here.
সাউন্ড দিত
Okay, so there is some technical problem in the video. So maybe we first have the second talk, and then if you can resolve, then we can come back to the first talk. So the next talk, finding three subset division property for ciphers with the complex linear layers, and this is by Demoshmita Chakraborty.
C6. 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 Documents.
Thank you for the introduction. Hello everyone. I'm Indocrypt Talks and here is my work, finding three-subset division property for ciphers with complex linear layers. So here is a glimpse of my work. That first background knowledge about bit-based division property, bit-based division property using three subsets and some previous works. So, and then the motivation of our work and finding, after that the contributions of that model for binary linear layer and MIB model for keyword operation, and finally the automatic search algorithm and the applications on some block ciphers is that. So I'm starting with the background knowledge, that fundamental concept of division property, the bit-based division property. So suppose we are starting with the set X, is a multi-set of F to N, and we are giving some property on the set X, the K, just saying the property K. Okay, so this is also a subset of F to N. Now X has, we are saying that X has division property D. So D, what is your notation? So X has some property with respect to the F X. If it fulfills this condition, so the sum of phi u x, x belongs to x is unknown. If there exists some k belongs to k, satisfying u successor of k and 0 otherwise. So the definitions is like this: phi u x is the monomial actually, and u successor of k means for all u I greater equal to k. So actually we are having a set X and which has some property K, and with respect to this I am dividing the space F to N into two parts like this for all those U's, such that U is satisfying this property U greater or equal to K, where K belongs to K, satisfying this property. So XOR sum of phi u x is unknown. So for those U's satisfying this property U greater or equal to K, so XOR sum is unknown, and for all other U's the XOR sum of X is 0. So I'm actually, they proposed this idea in Todo et al. By FSC 2016. So the idea is about that we are dividing the F2N set into two parts, unknown and 0. So this is the fundamental concept, but the accuracy is not perfect here. So on that same work, Todo et al. At FSC 2016, they proposed another concept which is called bit-based division property using three subsets. So the name says it all, that somehow like the previous where we are dividing the F2N space into two parts. So here somehow we are dividing the F2N space into three parts. So how we are doing this? So X is a multi-set whose value is some F2N, and here we are defining the property using two sets K and L. K into two sets, subset of F2N, and this multi-set X I am defining some property KL. So using this property, I am again dividing the space F2N into three parts for all those U, such that U is successor of K. For all those U's or sum of U is unknown. So those U's I am in the unknown part, and for all the other U's, so for the rest of the part I am dividing into two sets, is 0 and 1. So XOR sum of phi x is 0 and 1. So for all those L, rest of the L, where U is equal to L, so U belongs to the set L. For this XOR sum of phi u x is 1 and otherwise. So for all those U's which are not successor of K and as well as U doesn't belongs to L, for those cases XOR sum of phi u x is 0. So here I'm dividing this space into 3 parts like this. So this concept is the highlight of our work. So now here comes to the next part. So with all these definitions, what we are actually going to do. So suppose we have a set of plaintext set X multi-set we are starting with, and it has some property, 3 subset division property initial. So now suppose I'm applying some functions over the set X, F1, F2, like this. So now the set is propagating through these functions. Now I am interested, when we are interested in seeing that how this, how the sets is propagating through the functions, not like that, how the property is propagating through the functions, we are interested to see that. So suppose X is the input multiset which has the initial BDPT. So 3 subset division property, bitwise division property using 3 subset, we can abbreviation is BDPT. So initial property is that K0 L0. I'm starting with some initial property, and after the propagation, around propagation, there's some set say KRL. So this is the propagation, that how from starting one set with respect to the functions, around functions, how the property is propagating. Now, here we are seeing some notation. So now here we are dividing the, suppose a block cipher round function. So there will be the S-box, sensor, and Feistel or SPL. In those cases, those functions, and some keys or operation. So for a round functions fi, all the functions excepting the round functions, I denote it as sub fei, and for the keys or operation, I am denoting it as fai. So how the property is propagating through a functions, for all the public functions, that is in the round function, excepting the keys or, this is propagating independently, we can see. So there is no dependencies for K0 star, there is no dependency of the elements in L0. So they are propagating independently. But here comes, we can see that for the keys or operation, there is some dependencies is there. So from K1, K0 star, so from K0 star we cannot directly compute from the elements of K1 from K0 star. So there is some dependencies for the keys or operation, but for the rest of the things, like this. So we call this is an R round. So applying the R round functions over this initial property set, the R round BDPT trail. So we call it as a BDPT trail kind of a path. So starting from the case point K0 L0, the initial property, and is propagating through the functions FEI, FTI. The composition of this function is the round function, and like this. So this means that for any element, say Ki, Li, so suppose K1, L1, for this element K1, L1, there must exist. So this element K1, L1 is actually constructed from this K0, L0 for these functions. So how we can construct it for K1, L, Ki, Li from the elements Ki minus 1, Li minus 1, that we are going to see. So the propagation rule. So we are starting with a set X and its property, and now we are seeing the propagation of property. So as I have told earlier, that for the public functions, the propagation KL are independently evaluated, such as copies or S boxes, all those functions. But secret, in the secret round keys dot, then the computation begins. So how when the secret keys ordering is happened, so how the set, the output BDPT set is constructed. So that is the rule. So suppose before the keys ordering, the set is KL, okay. So that K bar L bar type of set, and after that, so KL, and the output set after the keys ordering K dash L dash, and suppose for the simplicity I'm considering that only at the ith bit the secret key bit is ZOR. So the output set has division property T K dash L dash, and this is of the form like this. That's L dash is equal to L, but for the K dash, there are two operations. So K dash, first we are constructing some new elements from each elements of L with this idea that as the key sorting operation is happened at the ith bit, so we are checking that if the ith bit Li is equal to 0, we make it 1 and then fit to the set K dash and the previous K set. So that is a union of two sets. So the previous K sets and some new elements which is constructed from the L set. So this clearly shows that there is a transition of elements between the set L from the set L KL and the set K dash T dash. Now the question arises that how to model this key-sort operation efficiently. So we have to somehow model these things, that transition of element, because whenever this is independently evaluation of public functions, that is fine. That is well modeled for copies or an SBOS functions already. But what about the key-sort operation? And the second point is it possible to construct an efficient automatic search algorithm for this 3 subset division property propagation? So now I will answer these questions gradually. So now comes to some previous works. So first previous work in CTRSA 2019, Hu et al. They proposed some definition called variant 3 subset division property, which is actually, this definition is actually between the 2 subset division property and 3 subset division property, in between that, because its accuracy is less than the 3 subset division property, but somehow it is better than 2 subset division property. And they applied on several block ciphers with simple bit permutation there. But as I say that it sacrifices some accuracy of bidding. It's not exactly 3 subset division property. And at the Asiacrypt 2019, Wang et al., they proposed an algorithm to construct the BDBD propagation. But in order to do that, they actually each round function, they have divided into several appropriate parts and convert the BDBD propagation into that 2 subset division property propagation, and then they applied on some several block ciphers with simple bit permutations, just like present, Simon, gifts, like this. So, but so that is fine. But when it comes to the block ciphers with complex linear layers, such as AES or LED or say skinny, this type of ciphers, so then applying this algorithm on these ciphers is very, very difficult. So this is not efficient model, and until now there is no accurate method to apply 3 subset division property on the ciphers with complex linear layers. So now our focus is on the block ciphers with complex linear layers. So why we focus on that? That's our motivation, one of our motivation, that I have said the many important cipher takes a complex linear layer as their diffusion layer. So what do you mean by complex linear layer? So for the block ciphers, complex linear layer means they have a mixed column operation. So after that SBOX and masking and all, they are applying the state with some mixed column diffusion matrix. So not only the simple bit permutation, and we can divide this complex linear layer into 2 parts as well, that for the binary linear layer and non-binary linear layer. So if the diffusion matrix is called binary matrix, so binary linear layer, and for AES LED it is non-binary linear layer. So what is binary linear layer? I come to that definition. So the second is this 3 subset division property is currently the most accurate method to find integral distribution on block ciphers. And as I said, that no perfect method is evaluate the security of ciphers with complex linear layers. So now here comes to our work. So first of all, I am going to construct some BDBD model for the binary linear layer. So what is a binary matrix? So mixed column matrix M. This belongs to Mij S cross S F2 to the power n. So Mij belongs to F2 to the power n. or M. So if this Mij is either 0 or 1, that is either 0 polynomial or constant polynomial 1. So for this, we call this M is a binary linear layer. For example, Skinny, Midori, Prince, Mantis, those block ciphers. And for those block ciphers such as AES, this Mij is not only 0 and 1, the polynomial is not constant polynomial. Like this for the AES and LED. So now I'm concentrating on the binary linear layer. So here our Mij is 0 or 1 either. So from M we are constructing a primitive matrix. So the matrix M, each element is from Galois field 2 to the power M. So I am converting this M with a binary representation of it. Okay, so we construct M dash where M dash Ij, this belongs to F2N process. So the primitive matrix with respect to the irreducible polynomial of GF to the power n. So for example, suppose I have taken a small matrix, so M. Suppose M is there. This is actually the mixed column matrix. No, that's not like this. This is a similar structure as Mantis mixed column operation. So suppose we have this thing. So for 0 and 1, this belongs to F2 square. Okay, so like this. So from this we can construct the primitive matrix is of the form like this. So here every 0 or 1 belongs to F2. From this we can construct this primitive matrix. And here it comes to a very important property of if we start with M as a binary matrix, so other than 0 and there is no other element. The rows of the primitive matrix corresponding to this M. So rows of the primitive matrix, we can divide it to the different cosets with this property that the rows in different cosets have no common non-zero entities in the same column. So as we can see that the 0th row, 2nd row, 4th row, and the 6th row, if I can make two cosets of 0, 2, 4, and 6, and another coset is 1, 3, 5, and 7, they have no common non-zero entries in the same column, as we can see. So this is a key feature of the binary matrix of this form. So exploiting this feature, we are going to model somehow. So suppose we have the initial state at X, and we are applying the M dashed matrix, mixed column matrix, and we got the output state as Y. So for this example, this X and Y belongs to F2A. So applying. So now from this structure, we can see that. So for the outputs bit Y0, Y2, Y4, Y8, these bits only depends on the bits X0, X2, X4, X8, and this is true for also X1, X3, Y1, Y3, Y5, Y7. Actually, applying this matrix M dash to a vector X is actually equivalent to performing the 4-bit S box of algebraic degree 1 in parallel, like this. So Y0, Y2, Y4, Y6 depend on this. So I am actually dividing this whole 8-bit segment into two parts, and then this is actually the parallel application of two 4-bit S boxes of algebraic degree 1 in parallel. Now we have the exact BDBD propagation model of S box of BDBD propagation in literature. So using this thing, so I'm dividing these two parts and using the idea existing for constructing the division trails, BDBD trail for the S box, and the linear inequalities whose feasible solution are exactly those BDBD trail can be constructed using this idea. And this is the accurate model. And the accurate division trail can be constructed. So now the second part of our contribution, then what will be the BDBD will be modeled for keys-or operation. So as I have told that for the keys-or operation, there is a transition of elements. So suppose we are starting with the division set, say ki minus 1 star, li minus 1 star, and after keys-or operation, this will be ki li. So where the ith keys-or operation is fki. So according to the rule, I'm dividing this into two operations. So for FKI, as I have explained the keys or operation rule. So for the first what happens? So for the elements in Li minus star, for each elements of Li minus 1 star, they are constructed some new elements, and those new elements and the elements in Ki dash is union to construct the set Ki. So I'm dividing it into parts. F1i, one function where the new elements is produced from Li minus 1 star, which is written in Li minus 1 dash. And after getting this Li minus 1 dash, I'm making the union of these two sets, Ki minus 1 star and Li minus 1 star, which is the function is F2i, and get that Li. So now to model these keys or operation FKI, it is sufficient to model that F1i function and F2i function. So first modeling F1i functions that for an n-bit block cipher, suppose the round key XOR is the leftmost edge bit for without loss of generality, I am assuming. And so the linear inequalities corresponding to the F1 function is that I'm not going much into that how we can I construct these inequalities. So for detailed analysis, please refer to the paper. And for F2i model, that is actually basically modeling the union operation. So I define a function g, which is of the form like this, where lambda 0, lambda 1 is take either the value 1, 0 or 0, 1. And if we take 1, 0, then it will be the elements of Ki minus 1 star, and it will 1, 0. And for 0, 1, it will be the Li minus 1 star. So basically to model the union operation, it is sufficient to model the g functions. And so the following linear inequalities are sufficient to respect the proportion of g is of the form like this. And using this two, we actually successfully model the keys or operation in BDPT. And finally, the automatic search algorithm. So so all tools are here. So we are now going to construct the automatic search algorithm for BDPT propagation. In order to do that, first we construct a set of linear inequalities because we modeled it in MILP. So we have constructed a set of linear inequalities which actually characterizes the around BDPT propagation, starting from this division property initial, say K and L, and this is like of the form like this. So actually, so those linear inequalities, feasible solutions are actually these around BDPT trails of the form like this, and we got this L and constructed the MILP model of this form. We are actually minimizing over K0R, where KR is the final set, just to check whether there exists a unit vector in the set KR. So in order to do that, I construct one MILP model here, and another MILP model I construct. So the linear inequalities L star, which is constructed such that the feasible solution of all the division states in one subset, say A0 to LR, is of the form like this. This trails is actually represented by that linear equality L star, and the complete MILP model is like that, L star. And so two MILP model I have constructed, and now our automatic search algorithm. So the input is the around cipher and the initial division property and the bit number q, where q is from 0 to n minus 1. That which means that which bit I want to see the parity. So that bit I am that actually represented by q. So to check all the bits for all the n bits, we have to run this algorithm n times, and algorithm output is 0, 1 or unknown. So what will be the parity of this? And for the algorithm is like that. First we construct the MILP model MKL, and search if the qth unit vector belongs to the KR or not. If it belongs to the KR, then actually from the definition, directly from the definition it follows, then we return unknown. And if it doesn't belongs to KR, then we construct the MILP model ML and check whether EQ belongs to LR or not. If EQ belongs to LR, then exactly directly from the definition we can say that the parity of this bit is 0. And if not, if EQ doesn't belongs to KR but EQ belongs to LR, then we count the number of solution or all the physical solutions in ML, and if the count is even, then we return 0, and if the count is 1, we return odd, we return 1 as the parity. And these are the correctness proof of the algorithm. There's if the number of division trails from, say, starting from L to EQ is even, then this will be odd and array. So these are the kind of proof ideas. So first we prove a claim, and then using this claim we can prove this theorem. So I cannot go much into this proof. Please refer to the paper. And finally, I have applied this idea on some block ciphers. So first the prints. So this is the block cipher, alpha reflection block cipher, have the binary linear layer, and got some improved result after 2.2 plus 2 rounds. So this is the forward round 2 and the backward round 2, and this is the middle round. So this is the BDPT of prints, and then finally we also applied on Dantics. This has a very similar structure to prints and got the improved result like this for 3 plus 3 round. And to complete our thing, so I also applied into some ciphers with non-binary linear layer as well. And in that case, I divide the non-binary layer, decompose that with copy and XOR operation, and using that, I've got some improved result on plain and block cipher pride. I applied also on Simon 102, but those integral distinguishers are in accordance with the previous best integral distinguishers. And these are the main results. Some future scopes are there that accurate BDPT propagation of ciphers with non-binary linear layers, and implementation of our model in SAT SMT, because these automatic tools are very popular nowadays. And finally, some efficient model to handle the intermediate L by using the automatic tool in case of BDPT propagation would be a very nice future work. So finally, I concluded my work. So I'm happy to hear any questions. Thank you.
Just one or two quick question. To clarify the contribution one, so this model works only for the binary.
Yeah, accurately.
And okay, this is the first thing. And can you go to slide 12, please? Yeah. So I think the second statement is not right, because there is a method called bit-based division property without unknown subset, which is the most accurate.
Yeah, but for finding integral distinguisher for block ciphers, still. Yeah, you can say for RAP it is applied.
Bit-based division property without unknown subset gives you exact rate, 0 or 1. There is no unknown.
Yeah, but how to apply it in for block ciphers? I'm saying that because there is no unknown case. Because for the public functions we can do this, but how to model this for the block ciphers where the secret key is Zori? So there the unknown parts is producing now. So how to model that? Yeah, bit-based division property without unknown subset is actually equivalent to the parity set concept as well. Okay, but how to model this for finding integral distinguishers for block ciphers?
Okay, I don't think I'm convinced. So, okay, let's see. We will discuss it later.
Okay.
This one.
Yeah.
So, whenever the output is in L, then you are counting number of solutions, right?
Yeah.
So, if you directly use, we prepare the model, solve it, and count the number of solutions. Is there any improvement in this method from that?
No, in which model? So I am counting the solution in ML model. So the ML for all the division trails from L in L. So your question one.
Whenever we are in L, we are counting the number of solutions.
So first we are checking that whether EQ belongs to KR or not. Okay. So if it belongs to KR, the discussion is over, because from the definition it follows that the XOR sum is unknown. So we can't do anything.
Yes.
So if not, then we have to check in the yeah. So then we have to.
Good question.
Thank you for the nice talk. I have one question. I didn't really understand your distinction between binary linear layer and non-binary linear layer, because like prints is not really, there's a difference between the linear layer and prints and or in Midori, for example.
Yeah, and
But,
maybe we do offline.
For Midori, for Mantis, the binary linear layer is similar to is exactly same to the Midori linear layer. So the matrix, the mixed column matrix is binary matrix.
Yes, but Prince is
No, Prince is also binary linear layer, but not exactly same as the Midori structure.
okay, maybe,
So the binary structure.
my understanding, Prince was not the binary linear layer, so this is why I wanted to understand what your exact definition.
Yeah, we can.
Thank you very much.
Okay, so I think let us thank once again. And let us just quickly check whether we can run the video. If we can succeed, then we can. Otherwise, we have to skip this talk.
স্ক্রিন শেয়ার করছিস না?
Hello everyone.
মির্জাকে বলতে শেয়ার কি করলি? স্ক্রিন শেয়ার করতে হবে না। আচ্ছা ঠিক আছে। আরে শেয়ার স্ক্রিন না করলে কি করে হবে? এবার বলতে হবে মির্জাকে বলতে হবে।
Okay, so I think we can start the video. So let us start it. And I hope I think there cannot be any question here after the video. So if you have any questions, we can directly ask to the authors. Okay, so authors are not available even in the live now. Please start.
Hello everyone. The topic for today's report is included integration discussion always important box. Authors are Chang monitoring Sunni and Away user Chang. Is the most widespread block library in the world. The security evaluation of ACE and the trusted addition of national cryptographic community. Chamber of series of excellent ideas and popularity techniques since its publication. The construction of the structure related to recovery attempts. Moreover, block cipher or surrounding the resolution of these cells and the pseudo-Roman implementation, which is the consumption in the security group of block cipher of these nodes, as functions and max, etc. Therefore, the existence of distinctions related to the series consequences and reports on the separately distinguishers of a previous paper. For integral distinguisher, Lemon and all presented on 3-1 integral distinguisher and extended to 4-1 by presenting a run at the beginning. Later, the high complexity is improved by focusing and all by partial sum technique. For truncation distinguishers, Berkeley and all introduced steps with shear cardinalities, which includes techniques based on truncation impossible declarations and integrals and special physics. Moreover, they observed the multiple of 8 property, which led to their work-based significant security distinguisher both by 1-8. Besides, Berkeley introduced mixture differential analysis on non-linear areas as life cycles. Recently, Paul and all illustrated how the well-known integral distinguisher on 3-1-8 examples of some of Japanese and extend to the truncated differential distinguishers 4, 5, and 6 1. Moreover, John et al. Proposed a new distinctions of 3 to 6 from A's, which is the fourth key independent distinction for 6 from A's, and was improved by Bolton et al. Posterior or mid-in-the-middle attacks also rely on distinguishers with different designs. We start with the analysis of full-round computer differential proposed in Bo and Al's work, which began with one active cell in the input difference and ended with one inactive cell in the output difference. With the value of the zero size in x_3 to the power of mistake be written and the value of 4 for x1, then for responding first line in x_0 to this 4 and 4 independent communication functions. Going to blind covering settings to get the probability of it. Once the difference of the zero spike in x_3 to the power of MC equals to 0, the difference of the zero spike in x_5 equals to 0 is probably 1. This zero difference is unaffected by AKSBSR operations, and the MC operation is omitted the former round. Then the difference between the probability of 4 round A's and a random function can be explored to build computer differential distribution. However, if we want to compute the coverage probability rather than an approximate one, we can to list all these differentials and characteristics from the full-round computer differential. Turn the probability of each one and take the mean value of them at the bottom right. Obviously, we come upon such a geometric calculation, and the correct issue is how to deal with inner submission in order to reduce complexity. A divide and combine technique is put forward, and the complexity is reduced by choosing the appropriate starting point in time memory trade-offs, especially for the ability of the 32-bit to 8-bit complex. An integrated idea is introduced and cuts down the complexity significantly. Then we can publish a tighter bond for several types or truncated differential distinguishers based on the ability of the block of X. We calculate all the input and output combinations of 4 rounds of computer difference and gives index hypothesis of the probability of 4-round computer differential. At the same time, from both sides comparison, it shows that we don't use a fraction of difference. Furthermore, we check some different 4-round computer differentials, which begin with one active cell and another with 2 inactive cells. Considering the conditional model, the statistical framework are defined and can construct new 4, 5, 6 round computer differential distinguishers. Moreover, we make some experimental verifications on 4 round A's and 4, 5, 6 round small A's. The results show that while operatives are reasonable and suitable for corporate block cover. By choosing the appropriate starting point, we present the whole algorithm based on divide and combine technique to calculate the probability of the 4-round computer differential distribution. The 4-round computer differential is divided into 4 parts. Only specifies them affect the probability. The most difficult part is part 3, for which we develop a new integrated export technique to further cut down the probability to cut down the complexity. The matching from the 4 bytes of FP in x_2 with the 0 spike in x_4 be taken on 32 bits to 8 bits super exports if we construct the DT directly, the complexity is 2 to the power of 64. Instead, we integrate from super exports into 3 16-bit to 8-bit methods, F1, F2, and F3. F1, F2 are 2 16-bit to 8-bit methods. In fact, both of them are XOR or 2 8-bit communications. Their DDTs can be calculated efficiently by merge table, installed as 2 pre-computation tables. Those F3 linear function 2 is the distribution function being constructed from the top 2 tables in a similar way, and the DDT of the whole function can be obtained. Once the DDT is obtained, the corresponding probability can be deduced. Algorithm's computational complexity is approximately 2 to the power of 37. We test the relation between the probability and the position of active in I0 and the inactive I5 upstream rounds. It is noted that the 256 combinations can be divided into 16 equivalent classes because of the structure of ACE. Based on the relation of cells in one column, we consider the joint distribution and achieve the probability corresponding to the case of 2 inactive cells in the same column and the output difference. The number of chosen plain text gaps is in reverse proportion to the absolute value of the difference of probability of a random computation on ACE or given success probability. In order to further improve the complexity of distribution type, we take advantage of computational probability to enlarge the absolute value of the bias between the probability of ACE and a random computation. The distribution of zero variable is still applicable to the galaxy as of statistical framework. Without too much in generality, we focus on the non-random antecedent of the distinguisher, and we consider full-round truncated differential distinguisher in conditional probability setting. By divide and combine opposites, we compute the probabilities of 2 truncated differential and compute the corresponding conditional probability. The data complexity of distinguisher type under conditional probability setting is 2 to the power of 30.56 chosen point tests, and time complexity is 2 to the power of 13.94 inclusions. Inspired by for and of construction, we extend our full-round computation to 5 round. Suppose the computation between the columns of the difference and data at -4 are independent of each other. We obtain the conditional probability for 5 round computation and can form a distribution type. Total complexity and time complexity are 2 to the power of 42.59 chosen plain text, and 2 to the power of 42.91 inclusions respectively. Based on the 5-round truncated differential, we extended to a 6-round truncated differential by adding 1 round at the beginning. The computation of the probability can be discussed in 2 pieces. The first is then the output difference of the first round, the difference of delta x_2 coincides with the input of the 5-round distribution. The second is then the difference of delta x_2 that will satisfy the first case, the response from different topics and the relevant nutrition. And the distribution type on 618 is given, which means 2 to the power of 62.88 tests, and 2 to the power of 63.4142 equations. This completes my report. The code used in this paper can be downloaded from the following website. And please email us if you have any questions. Thank you.
Thank you. So this is for to conclude today's technical session. There are two important announcements. We have a cultural program at 5:30. So all of you please be here by 5:20 so that we can start program in time. And then after the cultural program, we will move to banquet, which is in Altair. So we will go together. So after the cultural program, like around 7 p.m. we will move together. So please be here around that time. So that we can move together to Altair and we can start the lunch session and banquet. Okay, so that concludes today's technical session. So we'll be here at 5:20.